Part 3, Underfitting and Overfitting. So it is well known that as training progresses, that is with more iterations of the training data, your training error will almost monotonically decrease. But that's not the case for your test error. The test error will initially decrease, but after a while, it will eventually increase, which is kind of surprising, right? But that's very natural because at that point, your model has overfit to the training data. And the more you train your model on the same set of data, the more kind of close fit it is to the specifics of the training data, and it will hurt your model actually when you test it on some previously unseen data. And that is actually what we all care about. That is the generalization error, which is the error on previously unseen data. But because we don't know what kind of data will be tested on, that is, the test set is kind of blind to us. We have to kind of define or assume that test samples are drawn from a distribution, and then you can define the generalization error as the expectation of test error according to that distribution. In reality, we often use a small held out set that is a subset within training data to simulate test data, and then we can do early stopping. We'll say, oh, here you have to just stop training, right? Or if you train for, let's say, 50 iterations, and maybe iteration 20 is the iteration that achieves the best held out error rate, and then that is the model you should use for testing, for deploying into the real test case. Okay, the last slide we talked about underfitting or overfitting due to undertraining or overtraining. But a more common case of underfitting and overfitting is also because of model complexity. So underfitting can occur if you have an oversimplified model, right? If you remember the salmon versus sea bass example, a linear line is extremely simple. That is an oversimplified model, which causes underfitting. That is, it has pretty high error on the training set. And as Einstein famously said, everything should be made as simple as possible, but not simpler, right? On the other hand, overfitting can occur if you have overcomplicated model. And as the extreme case, a model that memorizes the whole training data would have no generalization power at all. So if you remember the salmon example, this very zigzag, nonlinear, highly nonlinear curve is definitely overfitting. Because if I give you a new example that you have not seen previously, chances are that you would mislabel it, even though you correctly labeled every single training data, right? Now, here is the example from regression, where your model complexity increases from polynomial of degree 0 to polynomial of degree 9, right? In degree 0, 1, and 2, you're underfitting. In degree of 9, you're overfitting, and your test error or generation error will go up to very high. So this is underfitting, this is underfitting, and with degree of 9, it's overfitting, right? So in both cases, like undertraining, overtraining versus model complexity being too high or too low, there's always a curve like this, where training data always kind of monotonically decreases, training error always monotonically decreases, and test error or generalization error kind of first decreases and then increases, right? So it's not good if you say, oh, my model has 0 error on my data. It doesn't mean anything. It's actually very bad if you say your model achieves 0 error on your data, because chances are that you have overfit to the data that you have. The best example is that I have some small training error, but I use the held out set to control the model complexity and to control overfitting, to control like overtraining. So ways to prevent overfitting. We talked about held out set a lot, right? So this is also called a dev set, a development set, or validation set. Another approach is regularization. It's explicit control of model complexity. We'll talk about that more in the SVM case. That is, we want to penalize a model that is too complicated. We explicitly prefer simpler models. But an even easier approach, a more direct approach, is to add more data, because there's never better data than more data, right? And overfitting is more likely to occur on small data. So think about this polynomial curve fitting again, right? So with these points, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points, it's likely to have overfitting if you have a polynomial degree of 9. But what if you have 15 data points instead of 10? Then polynomials of degree 9 is less overfitting, right? And then if you have 100 data points, then a polynomial degree 9 is perfect, right? So in these three cases, we have the same model complexity. Assuming the same model complexity, then with more data, it's definitely better, right? It prevents overfitting. Now, leave one out. So what is the best held out set? Maybe we can use a random subset. But what if that subset is not representative? Can we use every single subset? Yeah, that is the idea of leave one out. Let's say you have 10 training examples, and I would train on the first 9 and test on the 10th. And then train on 1, 2, 3, 4, 5, all the way to 8 and 10 and test on 9, and so on and so forth. Eventually train on 2 to 10 and test on 1. And then I average the validation errors on each of the left out pieces. Then I get the leave one out cross-validation error. It's called cross-validation because every single piece of the training data is used as the validation or dev set. Or if you have too many training examples, you cannot do this for every single one. You can divide the data into n folds, let's say 10 folds, and then you train on the first 9 folds and test on the 10th, and so on and so forth. So this is often the best approximation of generalization error, because every single example is used as a dev set.